This lesson we're going to look at floating point representation on computers. In other words, we're going to see how do computers store decimal values.
Namaste, my name is Ravi Reddy and welcome to my new video series entitled A Prequel to Programming. Things you should learn before you write your first line of code. Here I'll be trying to explain the fundamentals of computing and coding which are needed before you write your first line of code.
First, let's look at the two parts of decimal numbers. First is the fractional part, which we see out here. This is known as the mantissa, and then multiplied by 10 to the power minus 19. This minus 19 is known as the exponent. Let's look at what is known as the standard notation. A given number can be written in different forms with different mantissas and different exponents. By moving the decimal point around, we change the exponents. For example, the number 0.0985 into 10 to the power minus 9 can be written as 0.9850 into 10 to the power minus 10, or 9.8500 into 10 to the power minus 11, or 98.5 into 10 to the power minus 12. We need a standard notation, a standard form to store decimal number. So what we do is we store it in this form, 0.9850 into 10 to the power minus 10. What is the rule? The rule is that all the digits before the decimal point should be 0 here, and the first digit after the decimal point should be non-zero, that is 9 out here. So next we see how we can have a few numbers in standard notation. So we see here 46.5, it can be shown as represented as plus 0.465 into 10 to the power minus 2. The rule being that all digits to the left of the decimal point should be 0, and the first digit after the decimal point should be non-zero. The same here, minus 9.85, when it's represented here as minus 9850 into 10 to the power 9, we see that all the digits to the left of the decimal point are 0 and the first digit of the right is non-zero, which is 9. Similarly, minus 738.5 into 10 to the power minus 2 can be written as minus 0.738 into 10 to the power 1. Here again we say that all the digits to the left of the decimal point are 0 and the first digit on the right of the decimal point is non-zero. So these are all standard notations for the decimal numbers. Now let's look at binary decimals. So the binary decimal also has a mantissa part, something like this, and it also has an exponent out here. So let's look at them one by one. First we look at how to store the mantissa part of a binary decimal. For that we start looking at how to convert decimal fractions into binary. So let's review the process. If we are given 0.25 to base 10, we multiply it with a 2 and we get 0.5. We take the whole part of this, which is 0, and we keep the fractional part aside, 0.5. Then we take the fractional part here, 0.5 multiplied by 2, we get 1, the whole part is 1, fractional part is 0. So the process of conversion stops here because the fractional part is 0. So this works out to be 0.01 to base 2, which means 0.25 in base 10 is 0.01 to base 2. You can see here the place value of the first decimal place after the point is half, which is 1 by 2, and the next value is 1 by 4, which is equal to 0.25. In the same way, we can get 0.5 to the base 10 is 0.1 to base 2, 0.125 to base 10 is 0.001 to base 2, 0.75 to base 10 is 0.11 in base 2. Now let's look at another example, let's say 0.3 in base 10. When we take 0.3, let's go through the process, multiply by 2, we get 0.6, whole part is 0, fractional part is 0.6. 0.6 into 2, 1.2, whole part is 1, fraction part is 0.2. 0.2 into 2, 0.4, whole part is 0, fraction part is 0.4. 0.4 into 2, 0.8, whole part is 0, fraction part is 0.8. 0.8 into 2, 1.6, whole part is 1, fraction part is 0.6. Now you can see that these have started repeating. 0.6, 0.6. 0.6 into 2 is 1.2, whole part is 1, fraction part is 0, is 0.2. So now what is the binary values? It is 0, 1, 0, 0, 1, 1. So that is 0.01, 0, 0, 1, 1, 0, 0, 1, 1. So we see that we get a non-terminating fraction in base 2. So even terminating the decimal values in base 10 can convert to non-terminating binary fractions. So we need an infinite number of binary bits to be able to store this. The same way, if we try with 0.7, we go through the whole process and we get 1, 0, 1, 1, 0, 0, and the series starts repeating from here. So we see that this is equal to 0.1011, 0011, 0011, and this becomes a non-terminating binary decimal. Next, let's see 0.4. It converts to 0.01100110011 and becomes another non-terminating decimal value. Let's look at this process of converting from base 10 to base 2 in more detail. So here we have the number 0.625. I multiply that with 2, I get 1.25. I store the whole number 1 here and I get the 0.25 here. I multiply that with 2, I get 0.5. I put the whole part here, which is 0, and I put the fractional part here. Multiply with 2, 1, I put the whole part here, I get the fractional part 0. That's the end of the fraction. So 0.625 is 0.101 in base 2. Now let us try a different number. Let's try something like a 0.8. Now we see what happens is I take 0.8 here, multiply by 2, 1.6. 1 goes here, 0.6 comes here. Multiply 0.6 by 2, I get 1.2. 1 goes here, 0.2 comes here. Multiply that with 0.4, 0 goes here, 0.4 comes here. Multiply that with 2, 0.8. 0 comes here, 0.8 comes here. Multiply that with 2, 1.6. 1 comes here, 0.6 comes here, and so on and so forth. So we get this pattern 0.110011001100. So this is a non-terminating series of binary bits. For each of these bits, this is bit number 1 after the decimal point, bit number 2 after the point is here, 3, 4, 5, I have shown you the first 12 bits, this continues after that. What is the place value of bit number 1? The place value of bit number 1 is 2 raised to power minus 1, which is 1 by 2, which is 0.5. The place value of the second bit is 2 raised to power minus 2, that is 1 by 4, that is 0.25. Similarly, the place value of the third bit is 2 raised to power minus 3, which equals 1 by 8, which is shown out here. The place value of the fourth bit is 1 by 16, which is shown here. So this entire row shows you the place value of each of the bit. So we multiply the value of the bit with the place value and put it here. 1 into 0.5 is 0.5. 1 into 0.5 is 0.25, 0 into 0.125 is 0, 0 into 0.065 is 0, 1 into 0.3125 is 0.3125, and so on and so forth. These are the products. So now if I take the sum of the first 4 bits of the binary value, that is what is represented by this 1100, I get 0.75. This is the 4-bit value. If I take the sum of the first 8 bits up to here, this represents a value of 0.79688. Our original number was 0.8. So it comes a bit closer to 0.8, but it's still not there. If I take the sum of the first 12 bits, we get 0.79980, which comes a little closer to 0.8. So what do we see? We see that the more number of bits we take, the more accuracy we get. Let's take another value, 0.93. So 0.93 gives us the bit pattern 0.1110111000001. So if I take the sum of the first 4 bits, it gives a value of 0.875, which is not very accurate. If I take the sum of the first 8 bits, I get 0.92969, which comes a bit closer to the value of 0.93. If I take the sum of the first 12 bits, I get 0.92993, which comes close. So we see that even if we have a large number of bits, we may not get an accurate, exact representation of the number we want. It will always be approximated. The second observation is that the more bits we have, the more accurate is the representation. That means the more bits we have, the closer we come to the value which we want to represent. If we have only 4 bits, we have 0.875, which is not very close to 0.93. With 8 bits, we come a bit closer. With 12 bits, we come even closer. Since we do not have an infinite number of bits, we have to take a conscious call on how many bits we are going to use to represent the fractional part of the binary number. The more the bits, the more accurate will be our representation. So what are some of the repercussions or the bad effects of this finite precision? Since we cannot store any binary fraction with infinite bits, we have to choose a finite number of bits for storage. And this causes a lot of mathematical problems. For example, simple mathematical identities stop working on the computer because of finite precision. For example, A divided by B multiplied by B may not work out to be equal to A. B plus A minus A may not work out to be equal to B. This is because of the finite precision which is available for the storage of floating point numbers. Even comparisons, A and B, when we try to compare, it's very difficult and very improbable they'll be equal. So we should not really compare for equality between two floating point values. What is a better way? We should compare whether they are close enough. That means absolute value of A minus B is less than some given small value. Maybe 1.0 E minus 8, that is 10 to the power minus 8 or 10 to the power minus 6, depending on the accuracy. So this is the meaning of A and B being almost equal. So we never compare for exact equality, because even if there is a difference of some bit in the 14th place, they will not compare to be equal. So this is the better way of comparing two floating point numbers. Now let's look at how we can represent binary fractions in the normalized form. So again, once again, we use the same rule that all the digits to the left of the decimal point should be 0, and the first digit after the decimal point should be non-zero. So 0.011 can convert to 0.11 into 2 to the power 1. 0.0011 converts to 0.11, 2 to the power 10. You can see these are values of an exponent in base 2. 0.0001 converts to 0.1 into 2 to the power 11. Again, this 11 is in base 2 is the number 3. 0.11 is 0.11 into 2 to the power 0. 1.1 is 0.11 into 2 to the power minus 1. 10.1 in base 2 is 0.101 into 2 to the power minus 10 in base 2, and so on and so forth. So what do we observe out here? We observe that in the normalized binary fractions, the first digit after the decimal point is always 1. This is not surprising. The rule we have is that the first digit after the decimal point should be non-zero. And in base 2, there are only two digits possible, 0 or 1. So if it is non-zero, the only possibility is that the first digit after the decimal is 1. So this gives us a very interesting trick. We do not have to store the first digit after the decimal point since it's always 1. We simply assume that it is 1. So this idea is known as an implied bit or a ghost bit. That means we will not store the first digit after the decimal point. We'll simply assume that it is 1 for all practical purposes. So this gives us an extra bit of storage without wasting any actual physical storage in the computer. But this creates a new problem. Since the first digit after the decimal point is always 1, whatever we have after that, 0.1 and some bits out here multiplied with 2 raised to any power is not equal to 0. Why? Because 2 raised to any power, positive or negative, is not 0. And that multiplied with this value, which is never 0 because of 0.1 and some bits here, we cannot represent 0 here. So this smart idea of using the ghost bit creates a new problem that 0 becomes non-representable. So therefore, we need to have some values need a denormalized mantissa, some values like the 0. So most of the standards use the combination of normalized and denormalized mantissa values. Next, we look at how to store the exponent. That is this exponent out here, 2 raised to the power 1001 base 2. So this is stored using what is called a biased exponent storage. So the first thing to note out here is that we do not use the usual 2's complement integer representation. That is, the standard schemes used for storing integers are not used here. We use a slightly different scheme, which is known as the biased exponent storage. So here, the actual exponent is e minus p. What is e? E is the stored value of the exponent. That is the exponent considered as an unsigned integer, and b is the bias value. So the exponent e is the stored value of the exponent as an unsigned integer, and from that we subtract b. For example, if the stored value is 250 as an unsigned integer, the bias is 127. The actual exponent for that value is 250 minus 127, that is 123. Now let's look at a hypothetical 8-bit floating point representation just to understand how the entire floating point representations work. So we will assume that we are going to store a floating point number in 8 bits. So we will keep 1 bit for the sign of the mantissa. We will reserve 2, 3, 4, 5 for storing the mantissa, and we will store the exponent in 6, 7, and 8. And of course, we will use the ghost bit. So we will assume that there is a ghost bit of 1 here. So effectively, our mantissa has 5 digits. That is the 1 ghost bit plus the 4 actual stored ones here. We will assume that the bias is 4 for the exponent storage. Now let's see what this means. This means that the mantissa values will go from 0.10000 to 0.11111. You can see that the first one is a ghost bit. The rest 4 are the values stored in positions 2, 3, 4, and 5. There will be a 1 bit used for the sign and 3 bits used for the exponent. Let's see a few examples in our hypothetical 8-bit floating point representation. Let's look at the 8 bits out here. So we have the 8 bits out here. Okay. So for each bit pattern, we'll interpret what is the binary value being stored. So suppose we have the binary pattern 0, 1, 1, 0, 0, 1, 0, 1. What does it mean? The first bit represents it's a positive number. So you can see that this is 1 indicates negative number, this is 0 indicates a positive number, and so on and so forth. So this is the sign bit. The next 4 bits out here indicate the mantissa. So 1100 indicates a mantissa of 11100. Please note that we added the ghost bit out here of 1, which is always assumed to be there. So these 4 bits of 1100 imply a mantissa of 0.11100. What is the exponent? 101. 101 is 5. So the actual stored value is 5. The bias is 4. 5 minus 4 plus 1. So this bit pattern of 0, 1, 1, 0, 0, 1, 0, 1 represents the value of plus 0.11100 into 2 raised to the power plus 1. Similarly, this bit pattern out here, the next bit pattern 1010011 represents a binary value of minus 0.101 into 2 raised to the power minus 1. You can see the exponent here is 011, which is 3, E is 3, B is 4, 3 minus 4 is minus 1. So this represents an exponent of minus 1 here. Next one is this number out here, 0000111. So this indicates a number of plus 0.10000 and an exponent of 7 minus 4, exponent of 3. The next number is 1100001. This indicates a mantissa of minus 0.11000 and an exponent of minus 3. The bit pattern 0111110 will indicate a binary value of 0.11111 into 2 raised to the power 2, and the bit pattern and the last bit pattern given here 1000000 will indicate a binary value of minus 0.1 into 2 raised to the power minus 4. So this should give an idea of how the bit pattern represents a certain binary value. Now let's look at the next important part, that is, what is the smallest relative change in the mantissa. That is, we can have a change of 1 bit out here. Out here, this can go from 0 to 1. So this represents a change of 1 in 10,000, that is in base 2, that is in 2 to power minus 4. So this represents a change of 1 part in 2 raised to power 4, or 1 in 16, that is 0.0625. This smallest possible relative change in the mantissa is known as epsilon, or known as the machine accuracy. From this, we say that in base 2 we have 4 significant digits. So what is the significant digits in base 10? So we solve the equation 2 raised to power minus 4 is 10 to the power minus s. So s becomes equal to minus log to base 10 of 0.0625, that is 1.2042. We drop the fractional part and we get 1. So we get n sig, or the number of significant digits is 1 in base 10. What does it mean? It means that a 4-digit accuracy in base 2 is approximately equal to a 1-digit accuracy in base 10. So this depends on the number of bits in the mantissa of the binary storage. So we see that a 4-bit storage gives us only a 1-digit accuracy in base 10, which is really very poor, but that's what we have to expect from an 8-bit representation. Okay, so this answers the question, how many digits after the decimal point are significant? So here the answer is only 1. So now if we assume a bias of B, we get the maximum exponent possible is 4, the minimum exponent is minus 3. Here you will note that if we had used a standard 2's complement representation with 4 bits, okay, we would have obtained a range of -4 to +3. So the biased representation allows us to get one more positive value and instead of the additional negative value. So we are able to go up to 2 to the power 4 instead of only 2 to the power 3. This is the advantage of the biased exponent representation. So what is the maximum possible positive value? That is this bit pattern 0.11111. And what is the maximum exponent? 2 to the power 4. So that is approximately 16. What is the minimum positive value? We put all the 4 Mantissa bits to 0. We get 0.1 into 2 to the power -3, that is 2 to the power -4, that is 0.0625. How many values are there? That means how many representable values are there? In maths, we learn that there are infinite number of real values between any two real values. But in the computer representation, because of the choice of a finite number of bits in the Mantissa and a finite range of the exponent, there are only a small range of values which can be represented exactly. All other values are approximated. So we can see that for a given value of n, given value of exponent, we can have 16 values for the Mantissa for each value of the exponent and for each value of the sign bit. So 8 values of exponent from -3 to 4. So we get a total of 2 to the power 8 representable values for an 8-bit representation, which makes sense because there are 2 to the power 8 possible combinations and permutations of the binary values for 8 bits. Now, what about the spacing between the values? So we can see that between 2 and 4, we have got 16 representable values. Between 8 and 16, we got 16 representable values. And the same way between 0.125 and 0.25, we got 16 representable values. So we see that for the smaller exponents which represent values near 0, there are many small values near 0 and very few values away from 0. And having a lot of values near 0 is not very useful, but this happens to be one of the weaknesses of this particular method of representing floating point numbers. Let's go through the summary of what we see in the 8-bit floating point data type, which we just designed. We have 5 bits in the Mantissa, including the ghost bit. We have 3 bits in the exponent. That means 8 different exponents are possible. Total number of bytes used is 1, that is 8 bits. Epsilon, which is the smallest change, relative change, is 2 raised to the power -4. That you can calculate from this value 5 here, subtract 1, you get 4, 2 raised to the power -4 gives you epsilon. Then once you convert this 4 into the number of significant digits, by using this formula, you get number of significant digits is 1 in base 10. The maximum exponent in base 2 is 4, minimum exponent is -3. When you convert this to base 10, the effective exponents become 10 raised to the power 1 and 10 raised to the power 0. The smallest possible value which can be stored is 2 raised to the power -4, 0.0625. The largest value is 2 raised to the power 4, 16 is the largest value. So if we have a floating point representation which can only represent values between -16 and +16 and having an accuracy of only 1 digit, it's very clear it's not going to be very practical. We studied this 8-bit floating point data type just to understand how the representation works. Now let's look at some of the standard representations used for floating point. Now, if everyone had their own standards in terms of Mantissas and exponents and the bias values and whether to use ghost bit or not, it would become very difficult to exchange programs and run them on computers. So therefore, we have the IEEE 754 standard, which is the international standard for floating point representation. In addition to floating points, it also has proper support for storage of plus infinity and minus infinity. And it also has support for not a number or undefined. What is undefined? For example, if you try to get the square root of -3, there is no number, so it will return an undefined value. The IEEE standard also supports a plus 0.0 and a minus 0.0, the two separate representations, but when you compare them, it makes sure they compare as equal. Now, how does it support all these infinity and minus infinity and undefined values? This is done using special values of the exponent. Some values of the exponent are reserved for indicating all these special numbers. Why is the IEEE 754 standard needed? The IEEE 754 standard makes sure that we get hardware support for floating point operations at microprocessor level. Software level emulation is slow. We can't write our own software to work on the addition, subtraction, multiplication, and division of our own floating point numbers. So maintaining a standard makes sure that we can do all the mathematical operations on the chip level using hardware support, which is extremely fast as compared to software implementation. So let's look at the features of the 32-bit IEEE standard. This is the kind of the lowest precision floating point standard in IEEE. This uses a 24-bit Mantissa and an 8-bit exponent. That means 24 plus 8, 32 bits, that is totally 4 bytes. The epsilon value can be calculated from here. Number of bits is 24, epsilon is 2 raised to power minus 23, 1.192 e to power minus 7. From this, we can calculate the number of significant digits. That works out to be 6. So if you are looking at calculations where a 6-digit accuracy is sufficient for you, this will work fine for you. The exponents in base 2 go from 128 to minus 125. Please note that minus 126 and minus 127 are not used. These numbers are reserved for the special representations of plus infinities, minus infinity, and not a number undefined. Coming back to the exponents, having an exponent of 128 to minus 125 converts to an exponent of 38 to minus 37 in base 10. The smallest representable value is 2 raised to power minus 126, which is this value. The largest value is 2 raised to power 128, which is 3.4 into 10 to power 38. So having values from minus 10 to power 38 to plus 10 to power 38 gives you sufficient range of values for most mathematical calculations, and this should be sufficient for you. However, if you want a slightly more accurate one, you can use the 64-bit IEEE standard known as the standard double. So here we have 53 bits in the Mantissa, 11 bits in the exponent, 64 bits total. Epsilon is 2 raised to power minus 52. You get 15 significant digits in base 10, which can be used for very highly accurate calculations in your program. The exponents range from minus 1021 to 1024. Once again, minus 1022 and minus 1023 are reserved for the special patterns. The exponents in base 10 range from minus 307 to 308, which is a huge range of values. And the smallest values are 2.22 e to power minus 308, and large value is plus 308. Apart from this, there is a 80-bit standard which is also implemented in many chips, but it depends on the hardware you're using. This is a pretty old standard. This is known as the 80-bit IEEE standard, but it actually is stored in 96 bits on most computers. So there are 64 bits in the Mantissa and 15 bits in the exponent. Totally, the 96 bits are used to store. The epsilon value is 2 to the power minus 63. You get around 18 significant digits. So between the 64-bit and the 80-bit, there's not much increase in the number of significant digits. It goes up from 15 to 18. Where you get a huge change is in the exponents. The exponent range now goes from -4931 to 4932, which is a huge jump from the 64-bit. So if you are ever doing any calculation where you want to use a larger range of exponents, you need the 80-bit IEEE standard. Otherwise, the 32-bit and the 64-bit IEEE standards should be more than sufficient for most of your work on most of your programs. Thank you very much.
Please subscribe to my channel and hit the bell so that you will get notifications of my future videos. Thank you.